They gave me a new, they updated my Zoom, I think. It looks a little different. We'll do a share content. All right. And we'll go to notes. And I want to go back to our quant notes from last time. Because we were introducing this electrochemical cell. So that's kind of where I wanted to start so we could make sure we're all on the same page with that, because that's what we're going to be building out on today. Okay. All right, I think lab went reasonably well yesterday. I think everybody got through standardization, which is good. And then as for next time, we're going to actually generate our precipitates. So you'll have an unknown next time to work with. You'll go ahead and get that unknown diluted down, and then there's a procedure there to get it precipitated. So the whole goal for next lab is to get the unknown precipitate made, and then we're going to let that digest over the week. So then the last day is going to be a busy day because you're going to collect that unknown, you're going to clean it, and then you're going to redissolve it and titrate it. So that'll be week 3. All right, hopefully everybody also saw the example of an abstract that I put up over at D2L. I'm going to maybe get another one. I was thinking about grabbing one from Analyt, which is more of an experiment that's kind of similar to what we do. It'll be an instrumentation thing as opposed to a titration, but the language will be a little easier to understand. So I think I'm going to maybe reproduce one of those that a student wrote in my Analyt class from last semester. So you guys can look at that as the second example. So probably by Friday, I should probably have that up. So you'll have 2 examples to work from. All right, so remember that's due next Tuesday in lab. And remember, there won't be any quiz next Tuesday in lab because you got an abstract due. Okay, so we were talking about batteries last time. So when we utilize a battery, otherwise known as a galvanic cell, what we're talking about is a redox reaction. Okay, so we went back and talked about the definition of a redox reaction. We said that's a reaction where electrons are being transferred between 2 reactants. So one reactant is losing electrons, and that reactant, of course, gets oxidized, and the other reactant is gaining those electrons which were lost, which is then the reduction side. So we could write a oxidation half reaction showing the loss of electrons, or a reduction half reaction showing the gain of electrons. And we're going to do that here for the galvanic cell as well. So the idea here behind a battery is that we can basically combine 2 redox reactions in 2 beakers here and kind of tie them together into what we call an electrochemical cell, or a galvanic cell in this case. All right. And the idea here, we said, is that we have to have a continuous flow of charge from one side of this thing to the other. So if you focus again over here on the left-hand side, okay, we said that the reaction that's going on the left-hand side is what we call the anode reaction, which is indicative of oxidation. So oxidation always occurs at the anode, okay? That's loss of electrons. So we see the reaction that goes with that. What we have here is zinc metal. So we have a zinc electrode in there, which you see dipped into the solution, being oxidized to form zinc 2 plus 2 electrons. Okay, so you can see the zinc 2 actually being let loose into solution from the zinc electrode, okay, because that's losing electrons. So that's my anode half reaction. Then on the other side, we have the cathode half reaction. So that's where reduction is taking place. So the cathode is the electrode or half cell where reduction always takes place. And in this case, what we're talking about is the gain of electrons by copper-2 to form copper metal. So we can see in that beaker what we have is copper-2 ion, which we placed into solution, say as a soluble copper-2 salt, picking up 2 electrons to form copper metal, which actually plates out on the copper electrode. So again, where do the electrons come from to facilitate that reduction? They come from the left-hand side of the electrochemical cell, because zinc is giving them up over there. So you can see the electrons moving from left to right as zinc gives them up, so they can then be used over on the right-hand side for the reduction of the copper ion, okay? And then we said we have to have a salt bridge in there, which is that inverted U that you see that's connecting the two beakers together. And that's going to have an aqueous paste of some inert salt like potassium chloride that basically provides ions. Because again, we have to have flow of charge in all directions here. So if electrons can flow through the wire, I have to have ions flowing between the two solutions, and the salt bridge provides those ions so that I don't end up with a charge imbalance in my two beakers. Okay, so that's basically what's going on there. So that's a quick recap of what we talked about and put together last time on Monday. So any questions about the electrochemical cell in terms of what's happening there and the parts of it and all that good stuff? Everybody okay? And again, it's important to recognize that there's a voltage difference that basically is causing that electron flow to happen from left to right. And I can measure that on a voltmeter that I might put on the wire there between the two electrodes. So I can measure that potential energy or voltage difference that exists between those two half cells there. All right. And again, it's also important to recognize that if I'm dealing with a galvanic cell, I'm talking about a spontaneous reaction, okay? Now, this might be jumping ahead a little bit for you guys. I'm guessing that in dynamics, maybe I haven't hit the thermodynamics part yet. Has anybody seen the thermo there yet? Or are you guys still in like buffers and stuff?
Still in buffers.
Okay, good enough. So you haven't seen that yet. But basically, a spontaneous reaction is going to be exactly that. It's a reaction that happens as written spontaneously. And we have some thermodynamic parameters that will allow us to predict whether that's going to happen or not. We can talk about it in terms of entropy, but we can also talk about this in terms of something called Gibbs free energy, or delta G. Okay. So we're jumping ahead a little bit with regard to the thermodynamics, but it'll make more sense when you see it in dynamics. So again, let's just kind of recap what's going on in this cell. So at the anode, okay, what's happening at the anode? Oxidation is happening at the anode, okay? And here's the reaction. We'll just rewrite it here. I've got zinc solid. That's my electrode on the left, okay? And it's being oxidized to form zinc 2+, which is an aqueous solution. And in the process of doing that, we're leaving behind 2 electrons. Then at the cathode, reduction occurs. Okay, so that's the reaction we have on the right. So that's the copper 2+ in the right-hand beaker, an aqueous solution, picking up the 2 electrons that the zinc gave up to form the reduced copper metal. So that's Cu with no charge, and that's a solid copper metal. So each one of these is a half reaction, right? So I have an oxidation half reaction and I have a reduction half reaction. So you guys remember from balancing redox reactions, once I have 2 balanced half reactions, what do I do with them to get an overall reaction? Anybody remember? What do we do back in bonding?
Balance.
Add them.
Yeah, just add them up. So we balance, well, no, the electrons have to cancel. Remember, that's one of the requirements. If the electrons don't cancel, then we got to start throwing some whole number coefficients in there to make that happen. But basically, to get the overall cell reaction, which is what we call this, we're just going to cancel out anything we can cancel out and then write what we have left. So it's just like any redox reaction that we've seen before. Zinc ion plus copper 2. This is a nice easy one because it's easy to balance. Going to, it looks like zinc 2+. And we should get copper metal. Okay, so there's our balanced overall redox or cell reaction that we have going on in that electrochemical cell. Okay, and again, it's important to recognize that if this is a galvanic cell, which we stated that it is, this is a spontaneous reaction as written. Okay, Now, when we talk about something being spontaneous, this goes back to the thermodynamics that you guys are going to see in dynamics. There are two requirements that have to be met, and they can be tied together mathematically. But basically, one of these is that the delta S of the universe, and by the way, this is entropy, has to be greater than 0. Okay, so anybody remember what entropy is? I think we maybe touch on it back in bonding when we start to talk about thermodynamics there, but we don't go into any kind of real demonstration of it. Does anybody know what I'm talking about when I say entropy? A change in entropy, what's happening? Anybody know?
Change in order.
Yeah, basically it's a change in the order of the system. So basically, if I'm saying that the entropy is greater than 0, the entropy is increasing, and that tells me that the universe, the system, the surroundings, whatever it is I'm focusing on, is going to see an increase in disorder or a decrease in order. So think about, for example, a phase change, okay? So if I go from, say, a solid to a liquid through a phase change, and I melt that solid, what's happening to the order of the system? Is it increasing or decreasing?
Order's
Right?
decreasing.
Yeah, because what does a solid look like? A solid basically is a crystalline lattice, right? So all the atoms in the solid are locked together in the three-dimensional lattice. But if I go to a liquid, what's happening? I'm breaking up those bonds. So these guys are still close together, but they kind of have the ability to move around each other and flow, right? So what I've done is I've increased the disorder here. So what I've had in this situation is an increase in entropy of the system, okay? And in this case, I'm focusing on the system. But remember, when we talk about thermodynamics, we have a system and a surrounding that together combine to form the universe. And for a reaction to be spontaneous, the change in entropy of the universe has to be increasing. In other words, the universe has to be becoming more disordered, okay? And that could be a function of what the system's doing as well as the surroundings, because the universe is the combination of the two. Okay, so that's one way to predict spontaneity. We can look at it in terms of a change of entropy of everything, which is the universe. Or another alternative is I can talk about this other thermodynamic property called delta G. Okay, and delta G is what we call Gibbs free energy. Okay, so it's an energy term. So basically, the change in Gibbs free energy has to be less than 0 or negative. Okay, so I'm looking for a negative change in delta G. Okay, if I have that happening or an increase in the entropy of the universe, then I have a spontaneous process. Okay, so those are the two things that dictate from a thermodynamic perspective spontaneity. All right. Now, it turns out that delta G is really where we focus because delta G is an energy, okay? So if it's an energy, ultimately, I can relate it back to a potential energy such as voltage. So ultimately, in an electrochemical cell, we can relate a delta G and a voltage. And by looking at signs of things, I can predict whether a certain process is going to be spontaneous or not. Now, in this specific case I gave you, I'm telling you it's spontaneous. So based on that, you should be able to tell me the sign of the delta G for this reaction. Okay, you would know that the delta G for this reaction, for it to be spontaneous, has to be less than 0. Okay, and delta G's work just like, for example, standard enthalpies. Basically, it's a state function. So what that means is that I can calculate the delta G's for the products, and I can calculate the delta G's for the reactants, take the difference between them, look at the magnitude and the sign, and that'll tell me something about reaction spontaneity. Okay, so that's how this all kind of ties back into thermodynamics, which unfortunately you guys haven't quite seen yet. But now when you do see it in the next week, say, for example, in dynamics, you can say, oh yeah, I've seen enthalpy and entropy, and I can have a basic understanding of what they are. All right, so any questions about that, guys? Everybody okay?
Yep.
All right, good. So the next thing I want to talk about is line notation. So if you go back and you look at the electrochemical cell that I drew up there, that battery, that galvanic cell, I drew it in terms of 2 beakers, a wire, 2 electrodes, a salt bridge, stuff in solution. And that's kind of a complicated way of representing the electrochemical cell. It's actually what we've got, but it's kind of a complicated way of representing it. So the question now becomes, is there a way that I could generate a shorthand representation of the electrochemical cell so that you have all the information you would need to do calculations or to identify the cell without actually having to draw it out like this every time? And it turns out that's what line notation does for us. So it's a shorthand way of representing a full-on electrochemical cell. All right. So there's a couple of symbols that we need to kind of define before we do it. So we tend to use slashes and double slashes. Now a slash here represents a phase boundary. So that's exactly what it suggests. It's a boundary or an interface between 2 phases. Good example of that might be, for example, if I have a solid electrode dipped into a solution, okay, there's going to be a phase boundary between the solid and the liquid solution. Okay, so that's where we would utilize a single slash like that. The double slash represents the salt bridge. And the salt bridge, of course, is the physical entity that separates the 2 half cell reactions where each one takes place in a beaker. Now, do I need to specify what's in the salt bridge? No, I don't, because remember that just contains some inert ions that go back into solution to deal with any sort of charge imbalance that's occurring there. All right, so I don't need to specify what's in the salt bridge at all. Okay, I just need to know it's there. So for the cell that I showed above, here's the way we would actually represent it with line notation. So we'll kind of walk through it as we go. So I have the zinc solid, that's my zinc electrode that's on the left-hand side. And what's it in contact with? Well, it's in contact with zinc ion, right? So I have a phase boundary there. So in this case, what I could do is I could actually write the full-on salt that I put in there, or I could just represent this as zinc ion. But we'll say, for example, it's soluble zinc chloride, ZnCl2. Okay, because that's maybe the salt that I introduced the zinc 2+ into the solution with. Okay, now we have a salt bridge that separates that side from the cathodic or other side of the cell. And now notice that I'm kind of working from outside in and then inside back out. So now I go back to the solution phase. So I have the copper ion in solution. Maybe I brought that in as aqueous copper 2 sulfate. And then I have another phase boundary that takes me to the copper electrode. Okay, now here's the rule. Regardless of whether this is a spontaneous reaction or not, okay, the anode is always on the left of the salt bridge. Now remember, the anode is where oxidation takes place. The cathode half reaction is always on the right of the salt bridge. And that's where reduction takes place. Okay, so it doesn't matter whether this is a spontaneous cell or a non-spontaneous cell, that's always the way we're going to write this thing. Okay, so that's standard protocol. So the point is, we could specify in here, for example, the concentrations of the ions or the salts if we wanted to. And if we did that, we've pretty much got everything we need to know about this electrochemical cell. There's nothing that we don't know that wouldn't allow us to reproduce the cell. Okay, we know what electrodes are involved. We know what salts are involved. We could specify the concentrations of those salts. And other than that, it's just salt, bridge, and wire, right? So we're pretty much done. All right, so everybody see how this is kind of a good representation of the electrochemical cell without actually having to draw it all the way out? Everybody good? All right. So in most cases from here on out, we're going to use these line notations. So the next thing we want to talk about to kind of start tying all this together is this thing called the standard reduction potential. You knew we were going to start doing calculations sooner or later, right? And we have a symbol for that. We call that an E0. Okay, it's really an E naught, but we call it an E0. Now, here's why we need to know about this stuff. First of all, here's the question we could pose. Could we predict if a given cell reaction as we write it is spontaneous or not? Now, why would we care? Well, if we want to build a battery, for example, we'd want that reaction to be spontaneous, wouldn't we? Because if it's not a spontaneous reaction, we're not going to get any useful energy out of the battery. All right, so we want to be able to predict that. So how do we do it? Well, we're going to use these E0 values. So we're going to rank the species according to their ability to be reduced by way of E0. We'll see what I mean here in just a minute. When I say species, I'm talking about the various species involved in a given half reaction. And that's dictated by their E0 values, okay? So for example, if you look up at the cell up above, okay, what that's telling me is that the copper system on the right has a greater tendency thermodynamically toward reduction than the zinc system on the left. So in other words, if this is a spontaneous reaction, zinc would rather be oxidized, copper would rather be reduced, okay? And that must be shown to some degree in their relative E0 values. Okay, so in other words, if I know the E0 values for those two half reactions, I should be able to then predict that zinc would be the anode reaction and copper would be the cathode reaction for a spontaneous reaction. All right, so what is the E0? How would we define it? Well, we said it's a standard reduction potential. So it's the potential, which is a voltage, right? Which is just a potential energy associated with reduction of a species under standard thermodynamic conditions. That's what the not sign tells us. Now you see this back in bonding, right? Remember when we talk about standard enthalpies of, say, formation or reaction, these kinds of things? What did the little not sign above the delta H tell you? Well, it's telling you that we're making these measurements under standard conditions. So we're talking about specific conditions of temperature, pressure, and concentration. Okay, so what are those standard conditions? Standard thermodynamic temperature is 25 degrees Celsius, so that means the measurement's being made at room temperature. It's also 298 Kelvin if you want to do that in terms of Kelvin temperatures. Concentration, if it's a soluble species, has to be set at 1 molar concentration. That's standard concentration. And finally, pressure. Pressure standard is 1 bar, which is almost the equivalent of 1 atmosphere. Okay. So basically, we're talking about an atmosphere of pressure, room temperature, and 1 molar concentration. All right. So whenever you see E0 values, you know that those values are made under these specific conditions. All right, everybody good with that so far?
Yep.
Kind of remember that from like delta H's from last semester. Probably, hopefully, when you have that little knot up there, it's telling you you're dealing with standard conditions. Okay, so what's our rule? We talk about trying to develop a pecking order here, right? So here's the rule. The rule says the more positive the value of E0, the more readily a species is to be reduced. All right. So, for example, we can find these E0s in tables. And usually what we'll have there is an E0 value that goes with a half reaction. Okay, so in tables. I'll show you some of these in just a minute. I took a photograph of an E0 table from your textbook. But here's an example of one. Here's a half reaction. This is for the reduction of hydrogen ion. Okay, so hydrogen ion, of course, this is going to be at 1 molar concentration, can pick up an electron, always written as reductions because we call them standard reduction potentials. This has to happen at an electrode. So usually this is done at a platinum electrode. Hydrogen isn't just reduced by itself. You have to have an electrode in there to facilitate the reduction. And you end up reducing it to hydrogen gas, 1/2 H2 gas. So that's a half reaction, guys. Now, there will be an E0 attached to it, and the E0 attached to the reduction of hydrogen at platinum electrode is exactly 0 volts under standard conditions. Okay, and by the way, this has to be at 1 bar of pressure. Okay, and the whole thing has to be happening at 25 degrees C. All right, so you can see that we can define a half reaction, and we can define an E0 or measure an E0 that goes with that half reaction. Okay. So that's normally what we'd be looking for in situations like this. Now, let me just show you what a table of E0s might look like. Let me see if I can just pop out of here for a second, go over to my photographs. I think I have one there. Yeah, there it is. It's sideways, but you can kind of see it. So kind of turn your thing sideways so you can see what the thing looks like. But basically, here's what the table looks like here. And what you see is that we have a bunch of different half reactions here. The first one is actually going to be reduction of fluorine to fluoride. And you can move on down these various ones here. Look at the two that I have bracketed there. One of those is going to be the reduction of silver ion by 1 electron to form silver metal. The other one is reduction of copper 2+ by 2 electrons to form copper metal. Those are all reduction half reactions, right? Then below that, you see the hydrogen one that we just wrote. Okay. So essentially what we see here is that for any half reaction, we can define an E0. Okay. Now notice that there's a pecking order here. Notice that at the top, I have very positive E0s. And as I move down the table, the E0s become less positive and more negative. Okay, so what's that telling me? Well, the more positive the E0 is, the more likely that reduction reaction is going to happen. So for example, the top one, the reduction of the fluorine by 2 electrons to do 2 fluorides, okay, that's got an E0 of positive 2.89. That's pretty positive. So that tells me if I see that half reaction, chances are good that's going to be a reduction, okay? But what if I couple that with another half reaction further down, like for example, the hydrogen half reaction, okay? And then I have to decide, all right, if I want to have a galvanic cell here, I want a spontaneous process. This table is telling me which half reaction is the reduction half reaction and which half reaction is the oxidation half reaction, okay? So for a galvanic cell, obviously the fluorine reduction would be the reduction reaction because it's got the bigger, more positive E0. The hydrogen one at 0 is actually going to be the oxidation half reaction, isn't it? Because it has the less positive E0 of the two. So in fact, if I were to write that, I'd have to reverse the reaction, wouldn't I, to show it as an oxidation instead of a reduction. But the point is, you can see how I could use a table like this to predict for a given duo of half reactions, which one I think is going to be the reduction reaction and which one I think is going to be the oxidation half reaction for a galvanic or spontaneous cell. Everybody see what I did there? And we'll look at a few other ones here as well. But I just wanted to show you a typical table so you could see what these things look like. So I just, like I said, took a picture of this out of the textbook. Okay, let's see if I can get out of here. There we go. Go back over here. All right, so here's the deal. And we'll start out just under standard conditions because that's what these things represent. I can calculate an E0 for the cell reaction. Okay, here's how we do it. It's the E0 for the cathode. What happens at the cathode? Oxidation or reduction?
Reduction.
Yeah, reduction happens at the cathode. Minus the E0. And these are the E0s as we find them of the anode. And remember what happens at the anode. That's where oxidation occurs. Okay? Now, the assumption here is that both of these are actually written as reduction reactions. Because that's where we find them in the table, right? All right, so if we go back to our original galvanic cell that we talked about, let's write the two half reactions as reduction reactions. That's how we would find them in the table, right? So I could go to that table and I could find the E0 value and write it down, written as a reduction, because that's how we do it. So the E0 for that half reaction, written as I've written it, is minus 0.762 volts. Okay, now let's write the other half reaction that goes on there, again, as a reduction, because that's how we find it in the table. And we can again look up the E0 value in the table that goes with that half reaction. It's 0.339 volts. Okay, so again, keep in mind, both those E0 values came out of an E0 value table, as I just showed you, okay, for those specific half reactions. All right, so now take a look at this. For this to be a spontaneous reaction, could I predict by looking at those E0 values, which is going to be the reduction reaction and which is going to be the oxidation half reaction? Which of those two should be reduction for a spontaneous process? What does the rule say?
The zinc one, because it's less than 0.
Careful, you're going the other direction. Okay,
Would be the
remember,
copper.
yeah, it's going to be the copper because it has the bigger, more positive E0. Okay, So the more positive E0 is the reduction, right? Now zinc, written as a reduction, has a less positive, more negative E0. So it's going to be the oxidation half reaction. Okay. So now, if I want to calculate how much voltage I can get out of this cell under standard conditions, I can do that, right? I have an equation for that. So I know that my E0 cell is going to equal to the E0 for the cathode. What did we say that was? That's the 0.339, because that's where reduction takes place, minus that for the anode as written. So that's going to be minus a minus 0.762. So basically we end up adding those together, the negatives cancel, right? And you get 1.101 volts for the cell. Okay, so under standard conditions, all right, that electrochemical cell that we've defined before with the zinc and the copper is going to give you about 1.1 volts. All right, and notice that it's a positive voltage. And if you see a positive voltage, that's going to be spontaneous. Now, another way we could have done this is we could have done it by way of Hess's law. Okay, so let's just do it that way so you can see it actually work. Remember Hess's law from last semester when we added enthalpy reactions? So then when we have reactions that have enthalpies associated with them, we can manipulate the reactions and add up the enthalpies to get the overall enthalpy of a target reaction. And we're taking advantage of the fact that enthalpy here is a state function. So all we need to know is an initial set of conditions and a final set of conditions, which basically means if I have a table of enthalpies for the reactions, all I got to do is add them up. Okay, so we could do it the same way. Now, let's think about it in terms of what's actually happening here. If the zinc is the oxidation reaction, I could actually write the reaction that way, showing zinc actually being oxidized. So I'd have to reverse the reaction, wouldn't I? Which is how we originally wrote it. So here's my question. If I reverse the reaction compared to what I actually have above for it, right? So where's that reaction coming from? It's coming from that reaction up there, but I flipped it, didn't I? What do you think I need to do to the E0?
Change the sign.
Change the sign. So if I flip the reaction, it works just like enthalpies that way. If I actually flip the reaction, I have to change the sign on the E0. So it becomes 0.762 volts. Okay, now, do I need to do anything with the copper reaction? No, it's the reduction reaction. So I'm just going to leave it just as it is, right? So that's copper 2 plus, I'm just going to leave the aqueous out, plus 2 electrons going to copper metal. Now, do I need to change the sign on that E0?
No.
No, because I'm writing it exactly the way I found it in the table. So that stays positive. Okay, so in Hess's law, what do? I add the reactions, don't I? Okay, so we've done this before. We know what we're going to get. We're going to get our overall cell reaction here. So it's the zinc plus the copper 2 plus going to the zinc 2 plus. And this is exactly the same reaction we wrote earlier, right? For the overall cell reaction. Okay, so according to Hess's law now, if I add the reactions, what do I do with these zeros? In a Hess's law problem. Once I get these zeros manipulated, I add the reactions, what do I do with these zeros?
Multiply.
Don't multiply. You add them.
Oh.
Okay. Yeah, be careful, because sometimes it gets, you're thinking about like equilibrium constants, right? That's a different animal. So if you think back to Hess's law, you just add them up. If you add reactions, you add E zeros, okay? Because it's just a state function, just like a Gibbs free energy or an entropy or an enthalpy. So what you're going to get is the very same thing, 1.101. oops, 1.101 volts. Okay, so no matter which way you do it, you're going to get the same answer. The nice thing about the little pad equation that I give you up here, the one I'm going to circle, is that you don't have to manipulate anything. You don't have to figure out which reaction you have to flip and then remember to change the sign on the E0. You write both of the half reactions as reductions, and then you just plug in the E0s as you find them. Okay, so that's convenient. You don't have to think about what you have to do here. You don't have to turn it into a Hess's law problem, even though this is pretty much exactly what we're casting for you. Okay, so any questions about that so far? So here's your take home, guys. And I mentioned this before. When your E0 for your cell is greater than 0 or positive, that tells me the overall cell reaction is spontaneous. So what that tells me is that a positive E0 for the cell means we have a negative delta G for the cell. Okay, because remember, the overall change in Gibbs free energy has to be negative for a reaction to be spontaneous. So positive E0 means a negative delta G for the cell. Okay, so again, we're just satisfying basic thermodynamic requirements here. All right, so that's how we calculate a potential of a cell where everything is under standard conditions. Okay, now that's the easy one. You know what's going to happen though, guys. You know that under real laboratory conditions, are you always going to be under standard conditions? No, you're not. It's very rare that you're going to be able to actually run a reaction under standard conditions. What can vary? Temperature can vary, pressure can vary, and concentration can vary. Okay, so what I need is I need an equation that lets me actually calculate a cell potential under non-standard conditions. Okay, so that's the next thing we have to look at. All right, so here's what we do. We use something called the Nernst equation. Now, normally I would derive this for you. I'm not going to derive it here for you because it involves actually going back to some thermochemical definitions that we haven't talked about. I don't know whether you guys are actually going to get to this in dynamics or not. I'm guessing you may not, and that's absolutely okay. We will derive it when you get to analytic, because by that time you will have had all the delta S and the delta G stuff that you need to be able to come up with the derivation. Okay, but here's the Nernst equation. Here's what it says. It says that E, and this could be an E cell or an E half reaction, it doesn't matter which. I'm just going to call it an E, which is a potential. Okay, is equal to E0, okay, and we've seen what E0 means, minus R times T divided by N times big F times the natural log of capital K. Okay, so what are all these things? Okay, E is potential. That's measured potential. E naught, you know, that's a standard reduction potential. Then what else have we got? Well, we've got an R there. R is the good old gas constant. It's the thermodynamic gas constant. It's the 8.3141. So that's in terms of joules per mole Kelvin. That's a Kelvin down there, big K. T is Kelvin temperature. So you can see that T is suddenly a variable in here, right? So this is where we actually account for non-standard temperature. N, little n there is actually the number of electrons that gets transferred in the reaction. Stoichiometrically. So for example, if I look at a given half reaction, I look at the coefficient in front of the electron, whether it's 1 or 2 or 3 or whatever, that's what n is. F is a constant called the Faraday constant. It's kind of interesting. I'll mention it here in just a moment. Okay, and here's what it's equal to. 96,045 coulombs per mole of electrons. Okay, so what's a coulomb? Anybody heard of a coulomb before? Do you know what that is?
Isn't it a measure of charge?
Yeah, it's a measure of charge. So if you think about an electron, it's going to have a charge associated with it, and that charge could be measured in coulombs. Okay, so what we're talking about here is the number of coulombs or charge units per mole of electrons. So when you think about this, this is kind of Avogadro's number for electrons. Okay, this is Avogadro's number worth of charge here. Okay, so in a sense, we kind of use F like Avogadro's number when we're doing, for example, electrochemical stoichiometry. But rather than talking about the number of atoms per mole, we're talking about the amount of charge that we have per mole. Okay, so it's Avogadro's number for electrons. All right, and then finally, we've got big K. And you guys know what big K is. That's the equilibrium constant for the reaction. So normally we would express that in terms of the law of mass action, which you guys know how to do. As in any given electrochemical cell or half reaction, we got products and reactants, don't we? So we could express K in terms of equilibrium values or concentrations of products and reactants or partial pressures. All right. So how does this work? Well, what we end up doing, and this is what we'll come back and do on Monday, is I'm going to apply the Nernst equation individually to half reactions. Okay, so I can use the Nernst equation to get a potential, a measured potential, if you will, under non-standard conditions for any half reaction. So then if I have two half reactions, I'm going to calculate the potential of each half reaction. And then what we're going to do is we're going to swing back around and essentially add those up, kind of like we do in Hess's law, okay, to get the overall cell potential once I've got the potential calculated for each half reaction. So that's kind of the game plan. So I could give you, for example, an electrochemical cell. I could state the concentrations of the solution-based species there, the temperature, all that good stuff. And we'd have enough information now to be able to calculate using the Nernst equation, the overall potential of the cell under non-standard conditions. So that's what we're going to swing back around and do next time. All right, any questions, guys? Okay, I will see you guys on Monday then. So have a good weekend.
Alrighty, have a good one.
Thank you.